Our speaker today is Miodrag Iovanov. His research interests are non-commutative algebra, representation theory, quantum groups, combinatorics, and category theory. He will be speaking today on combinatorial Hopf algebras of multi-complexes. The floor is yours, Miodrag. Thank you for giving us a talk.
Okay, thank you very much for introduction. Thank you very much to you and all the other organizers for accommodating my talk. I've been enjoying myself very much coming to the talks here, and I hope I can, at least give something back. My talk today, I will perhaps be a little bit about graphs, but will be a little bit different than the talks that we've seen here because I'm not really a graph theorist. I have been interested in certain graph theoretical problems. So I'm trying to get more and more into perhaps combinatorics, which has been one of my first interests in mathematics. So I will talk about combinatorial half algebras, or the title that I've used on this particular presentation, Algebra of Multi-Complexes. And this is joint work with Jae-Young Jun. He was a postdoc at Iowa a couple of years ago, and he's now also in New York State, not far from here, just at New Paltz, just a couple of hours north, maybe even less. So um, let me just start by giving some initial motivation, which comes from the graph reconstruction conjectures. So just a definition, I'm pretty sure that this is something that everybody in this crowd is already very much aware of, but let's just start with a graph. And the vertex deck of G is defined to be a multiset. Let's call it D of G. And I want to put dv of G. So this notation here is going to be the multiset of isomorphous types of graphs obtained by removing one vertex at a time. So you take G and you take out V, one vertex at a time for V of G. And we just retain the isomorphous type, of course. And similarly, the edge deck, the so-called edge deck of G, is the multiset of isomorphous types of graphs obtained by removing one edge at a time. Um, so, of course, some graphs may repeat here, and if you just look at, maybe, let's say, like a star, something like a star graph like this, then if you remove one edge, this has four vertices and three edges. If you remove let's say one vertex at a time, um, you get just a graph that has this shape, three vertices and two arrows, and you get this three times, right? So you're removing each of the vertices, and then also if you remove the central vertex, you just get the totally disconnected graph on three vertices. So that would be the deck. So this appears three times. Sorry, but my screen is actually not great, so I can't do a very complicated notes. But just wanted to say that this one over here appears three times, and then the totally disconnected graph appears just once. So what are these vertex reconstruction, or these reconstruction conjectures? The reconstruction conjectures say that every graph can be reconstructed from its vertex deck. So if you know what isomorphous types of graphs appear when you remove one edge at a time, one vertex at a time, and you also know how many times those appear, then you can reconstruct the original graph. Or equivalently, you could say, given two graphs which have the same vertex deck, then the two original graphs have to be isomorphic. So that's the vertex reconstruction conjecture. The edge reconstruction conjecture says the same, but with the edge deck. So every graph can be reconstructed from the edge deck. Okay, so if you know what happens if you remove one edge at a time, you retain all these types of isomorphism of graphs. And you also retain the multiplicity with which each appears, then you should be able to reconstruct the original graph. Or equivalently, you could just say if you have two graphs that have the same edge deck, then the original graphs have to be the same, so isomorphic in the sense of isomorphism. Okay, let me just say if I may try to keep an eye on the chat, but if anybody has a question and I may not notice it in the chat, please feel free to let me know. Um, okay, so a few notes about these conjectures. There's also versions of these conjectures where you, instead of taking the multiset for the deck, for the vertex deck or the edge deck, instead of taking the multiset, you actually just take the actual set of isomorphisms. And there's also a conjecture that every graph can be reconstructed from that set, even if you forget the multiplicity. And every graph should be reconstructible from the edge deck, even without multiplicities. So some of the things that are known, it's known that the vertex reconstruction conjecture implies the edge reconstruction conjecture. So in the sense that if the vertex reconstruction is true, then the edge reconstruction, maybe you should call it question, but let's say conjecture, then that's also true. And the vertex reconstruction conjecture is known for many classes of graphs. I didn't really put in the full list here. I put in three, which are perhaps more more usual, like regular graphs, trees, disconnected graphs, but there are many other graphs for which is known. Many invariants are actually recognizable by the vertex deck. So for example, the number of vertices and edges, some of the polynomials that are associated to graphs, chromatic and polynomial and such. The degree sequence and many other things are recognizable from these features. So after all, this is supposed to be, I mean, suppose, one would like for this to be true. It's verified for graphs up to 11 vertices. The first time I saw this, I thought, well, this is so little. Why only up to 11 vertices? But then, even in this seminar, we've seen a number of talks where even particular classes of graphs, we've seen how many such graphs are there in those classes. So if you want to look at all the graphs, that's a huge computational challenge even for computers. And another interesting fact is that almost all graphs are reconstructible in the probabilistic sense. So the ratio, if you take graphs with up to n vertices, the ratio of reconstructible graphs up to the ratio to all graphs goes to 1 as n approaches infinity. So I don't really, I'm not a specialist. I don't really know how that is proved, but I think that's a paper in the 90s. So what I'd like to talk about, so that was our initial motivation in looking at what I'm going to say right now. So I'm going to be looking into some algebra. So I'm going to fix a field of characteristic 0, or just take k equals q. That's enough. And we want characteristic 0 to do combinatorics. And we're going to let hg be the span of the isomorphous types of graphs. So if I take two graphs, G and H, so this G index there should not be taken as a graph. That's just a letter which is supposed to be H is gonna come from the name of Hopf, and G is that this comes from graphs. So this is gonna be called a Hopf algebra of graphs. Um, so this is a vector space over Q, and it has a multiplication. You just take two graphs and you just concatenate them. So that means you put G and H together just plainly. And it has also another operation that goes sort of does the opposite thing that multiplication does. And whenever something does something that's dual or the opposite, you put a co in front of it. So this is a co-multiplication. So what does a co-multiplication do? It goes from this vector space Hg to the tensor product HDG tensor Hg. Everything is going to be over Q. All the tensors I write are going to be over Q. So in other words, if multiplication, smashes things together, co-multiplication splits things apart. That's a general, maybe a general rule of thumb. And this is what the co-multiplication does. It takes this G over here, and it breaks it up into all possible ways. You take all a sum over all the subsets of the vertex set, and you restrict the graph to X and to the complement. So by restriction, I mean I just take that set as usual, and you look at all the edges that exist in G between vertices in that X. So you have this formula. And here's an example. I tried to draw here. I tried to draw a couple of graphs, and later in the talk is going to be perhaps a little bit better. So the example is this triangle graph, and the star. I just wanted to use a star to say how it multiplies by another graph. This star graph, you just put them together. So the star, I put a star because I just wanted to show this is actually a multiplication, and the multiplication does nothing but putting them together. And then for co-multiplication, you take, let's say you take this graph here. So a graph with two vertices and one edge. So what you do, you split them in all possible ways, right? So one way of splitting it is empty set and everything. So the empty graph, the empty set will be considered as a graph here. So one of the ways is just empty set and the whole graph. Another way is to just split it in the middle, right? So just split it in the middle. So that will give you a point and a point. So that's and that appears twice because we're doing we're actually doing over all subsets of the vertices before removing labels. So and then at the end of the day, you just retain isomorphous types. Okay, so that means that you have either you do this as your set X, or you do this as your set X, okay, and the other one as the complement. So therefore you have twice times dot tensor dot, plus then there's also the possibility that the set X is the whole thing and tensor empty set. And of course, we expect that we'll have 2 to the n terms, so the sum of the coefficients sanity check should be 2 to the n. And here's another example. I took the triangle graph and I did the same for the triangle graph here just to see how this operation works. So you split it into empty set n times a triangle plus 3 times. Of course, if you split it like this, you get a dot and just a graph with 2 vertices and 1 line. And then you do the same. You actually can do this 3 ways. And then you can also do the set of cardinality 2 first times set of cardinality 1, and then a triangle and empty set. Okay, so we have, of course, 3 plus 3 plus 1 plus 1, that's 8. So, and that's, you see that if you have a complete graph, you're going to get just a nice combinatorial coefficients there. The binomial coefficients is what you get in that particular instance.
Miodrag,
So here,
I have a question.
2 other, perhaps, yes, yes.
So these are supposed to be isomorphism types. And it's apparent that an edge tensor, the empty graph, is isomorphic to the empty graph, tensor, and edge.
So
Right.
we think of, first of all, the H consists of the span of the formal span of the isomorphous types. Okay, now we're looking in H tensor H. In H tensor H, if I have the element V tensor W, that's not the same as the element W tensor V. So we are looking at, so we can't say that, we're not, what does it mean for 2 elements to be isomorphic, right? So we are just looking at these as elements in the tensor product. So for example, I have let's say, let me say, I have this element over here, right? And this element over here, these are distinct elements of the tensor product.
Okay, I understand that, but
Okay, it's like
slide, you
Mhm.
actually defined G times H as the graph which you get by putting G together with H.
yes, that's the multiplication,
Okay,
right? So we have two
different from,
operations on this space.
oh, I understand.
Yes, right.
Same as the
So
tensor
we have
product. Okay.
yeah. So we have
Yeah.
okay. So we have a multiplication. I know this is I'm trying to kind of go over some examples because this may be a somewhat different kind of a setup. I mean, um, we have just two operations on the set. We have a multiplication, which is just a multiplication as usual, associative, and we have something that does the opposite, and that's what I'm trying to do examples of this opposite thing. The multiplication, as you say, it's almost trivial if I could say so. The co-multiplication is doing these things. So intuitively, of course, what we're trying to do here is we have a set of, so this is a more general procedure. We have a set of general combinatorial objects which have an ability of getting put together and getting split apart. And we want to introduce algebraic maps which encodes these two operations, the assembly and also the disassembly information for these combinatorial objects. So that will be encoded in this. So for example, this co-multiplication that we see right here, this example of the triangle graph, this whole sum encodes all the information about disassembly of this graph into subgraphs somehow. So yeah, so let's yeah. Oh, thank you for the question. This is I'm really glad that you brought that up, because this is perhaps a setup that's may not be as usual outside of maybe a particular direction of algebra and algebraic combinatorics. So just a couple of other examples. I took the simplest example because I wanted to make an observation here. In this square that we see here, I have a graph. The graph consists of only one point. So sorry, the examples right now are quite trivial, but I think it's just aiding to help this structure. So the co-multiplication of this, you have a set with one element. The power set contains only the empty set and that element, so you'll have two terms. That's going to be the empty set tensor the point plus the point tensor the empty set. Okay, so we have this element, which again is an element in H tensor H. So hopefully my screen will allow me to actually say this. So this is always an element of H tensor H. And then the next example, which is the two dots graph, behaves very much like the example we had above with two dots and one arrow. So I have empty set tensor dot dot plus 2 times dot tensor dot plus the two dots tensor the empty set. So what I want to do is just a little exercise in just undergraduate algebra, or whatever type of algebra it would be to just take this equation that I have here and add it with this equation that I have right here. So I actually subtract them. So I'll subtract. Well, you could even add or subtract. That's you could do anything. But let's subtract the two equations. And what's noticeable here? Let me see. How can I get rid of this thing from the screen? Okay. So if you notice, so I take this equation over here and I subtract it with this equation over here. The central term dot tensor dot appears twice, and that cancels out. So all we have is empty set tensor this element that we started with, right? So empty set tensor that element plus that element tensor the empty set. And this is I misspoke in the beginning, and I kind of intentionally let it be like that. And we'll see that this will appear again. So I said all graphs should be reconstructible. Of course, I should have said all graphs with at least 3 vertices will be reconstructible, because if I have just 2 vertices, we just look at these 2 graphs, right? So the disconnected and the connected graph, and they have the same vertex deck, so you cannot reconstruct them. And we'll see that this will appear actually a little bit later. And the fact that the difference between these two has exactly a formula like this. So the co-multiplication gives you exactly this type of element, empty set tensor the element plus the element tensor empty set. That's going to appear in the algebraic reformulation of these questions. Um, so we can, if we look at these two elements, the dot and this difference, they have the same type of formula, exactly, empty set times the element plus the element times the empty set, tensor the empty set. So these types of elements are so-called primitive elements. An element that has this property is called primitive element, and they usually, they describe the structure of this algebra, which is a Hopf algebra. I haven't defined, but I'll just define that in a second. So Hopf algebras are exactly algebras that have two types of operations like this. You have a multiplication and a co-multiplication. They have to be compatible in the sense that the co-multiplication is a morphism of algebras. And remember that the co-multiplication goes from H to H tensor H. So I can require for this to be a morphism of algebras. And you also have to have an antipode, which in essence is kind of like an inverse function, but also it can be regarded as a type of a Möbius function. So just for a little bit of intuition, I'm just going to do a little bit of a digression into the world of Hopf algebras and derivations, so Lie theory and Lie algebras, so that I show that these type of primitive elements are in fact what are in fact derivations. So let's take just an algebra like polynomial, power series, or any kind of algebra, and you can consider derivations on this algebra and form a Lie algebra of derivations. And you can take this algebra, or you can take the universal enveloping algebra and consider that this algebra acts on A simply by, you take a derivation, d of A will be just d of A. And this U of L, has a multiplication, but it also has a co-multiplication. And I'm going to talk a little bit about this. So the general idea is that if you have such an H, a bialgebra, so a bialgebra again means you have two things. You have a multiplication and a co-multiplication. So if you have a co-multiplication, that means you have a map delta as above, which delta for each H gives us a sum of tensor monomials, hi tensor gi, right? So that has to be an element in H tensor H. Whenever you have something like this, you can act on an algebra, on this original algebra, and you require that the action has the following compatibility. So whenever you act with an H on a product of elements, you have that is equal to the same as acting with the first piece, so the hi on the first element, times the second piece on the second element. So let me consider two situations. So let's say you have such a bialgebra, and for example, suppose you have an element H for which delta of H is H tensor H. And let's write this axiom that I just wrote on this row here. Let's write it for this particular case. So the hi and gi are just H tensor H. I have just one element there, not two. What does it mean to have this equation here? Well, it means H dot AB is H acting on the first times H acting on the second. And now you see that this means H is a morphism, it acts as a morphism, right? And in the Hopf algebra world, this is called a group-like. So because if you think of H acting on something as just a map from A to A, well, this just says that H is in fact a morphism. So elements that have this simple kind of co-multiplication are in fact the morphisms or automorphisms even of the algebra. The second type of situation, when you have an element which acts exactly like this, delta of H is 1 tensor H plus H tensor 1. So this is exactly the type of elements that we have seen before. If you want to act with H on an A times B, according to the axiom that I have right here, that would be I have to act with 1 on the first element, and 1.A, 1 is supposed to act like identity always. So 1.A should be A, just be the identity. So A times H dot B plus, and then I have, so that's because I'm using the first element right here, 1 tensor H. And then when you act with the second element, h tensor 1, you apply h to A and identity to B, so you do nothing to B. And you see this is exactly a derivation, right? So if you write h dot B as, let's say this is some d of B, that just means that the action of h is a derivation of this algebra. So derivations correspond precisely to primitive elements in such Hopf algebras. So the primitive elements really are like derivations. You can think of whenever you have a primitive element somewhere as being some kind of a derivation on some abstract algebraic object. And sometimes, a lot of times, we can actually realize them as derivations if you want to. Um, so let me just give another example here of an algebra that has of an object that has both these multiplication and a co-multiplication. So this is going to be just polynomials, k of x1, x2, and you can either stop at 3, 5, or some n, or not just not stop and just put arbitrarily many variables here. And there is a co-multiplication, which is defined on the variables as delta of xn. So you define them to be primitive. The variables are defined, the co-multiplication on the variable is 1 tensor xn plus xn tensor 1. And this extends to all polynomial because we want delta to be a morphism. So since this algebra is commutative free, then I can freely extend this to all polynomials. And then, there's going to be some formulas involved. Okay, so I've taken probably a little bit too much time here, but I just wanted to explain the setup a little bit. And one of the things that you can do, you can reformulate the vertex reconstruction conjecture, in fact, to the following statement, that G minus H is not primitive if GH have at least 3 vertices. And now I want to just go back to the previous example that I computed right here. So this example, you see, we have an example of 2 graphs where the difference is actually a primitive element, and the 2 graphs cannot be reconstructed. And this is actually what happens in general. The vertex reconstruction conjecture can be reformulated to say G minus H is never a primitive element if G and H are distinct graphs, non-isomorphic graphs. Okay, so that's the algebraic reformulation. So that was a motivation for us to try to understand more about such type of combinatorial Hopf algebras. Classical results in the world of Hopf algebra say that this HG, since it's connected, it's graded, it's commutative, co-commutative, some words, has lots of nice properties, then actually this Hopf algebra, so this algebra is isomorphic to the algebra of polynomials. As an algebra, it's very easy to see that because you just use the isomorphous types of graphs and you just create freely spanned polynomials with them. So as an algebra is pretty obvious, but then this says not only as an algebra, but with this whole Hopf structure where you have co-multiplication and you have an antipode, as I said, that's also the case. So, what do we want then? I mean, if this is already recognized, well, we want to actually understand this, not just, okay, up to isomorphism, but we actually want to find a basis for the space of primitive elements, which is combinatorial. So something that has a combinatorial meaning, something that we can perhaps use in combinatorics problem. And we want to find cancellation and grouping free formulas for this, for the antipode. So these are actually a couple of questions which in the world of combinatorial Hopf algebras are sort of the primary type of questions that you would ask, and especially the second one with formulas for the antipode. So what is this antipode? So I'm going to try to explain a little bit intuitively what the antipode is, just by giving a few examples. So you take a group and you take a group algebra. This, in fact, is such a type of element, is a Hopf algebra. But the antipode, it's here is just giving by taking inverses. So that's something that's easy to understand. So this is what the analogy would be. And if you have a Lie algebra and you have the universal envelope in Lie algebra, the antipode is also very easy to describe. S of x is minus x for x in L, and then can be extended to the whole algebra. And in general, the antipode is something that satisfy a condition like this, where this epsilon is an augmentation map, and intuitively, this S is a Mobius type of function. It's kind of like a Mobius type of function, and it is actually the inverse of the identity map, kind of like the inverse of a zeta function in an appropriate convolution algebra, in the same way as Mobius functions are. So, and like Mobius functions, it can be found recursively. So what do I mean by this? So I'm going to take this highlighted equality here, this yellow highlighted equality on right here, and I want to compute the antipode for something. So I took the graph with this just V graph, so just 3 vertices and 2 arrows like this. And in these equations that I'm writing here, letters represent the graphs that they look like. So V represents this graph, I represents just the 2 vertices and 1 arrow. So first I wrote the formula for delta of V, and we have 3 vertices, so we expect to see 8 terms here. So the sum, let's see, the sum of the coefficients is 1, 2, 1, and then 2, 1, 1. So that's fine. That's 8. And we use this formula again. So this formula over here, you apply S on the first component and then identity on the second. So you apply the S on the first components here. You apply S on these graphs. And actually, you can also apply it on the second and leave the first one put. So that's the same. And then we obtain the formula that we see right here, starting on this row. And so we have all this. And if you look at this formula, we'll realize that S of V appears only here. So if I have managed to compute S of I, S of dot, S of empty set, S of 2 dots, and then I will have managed to compute V, and all those are actually graphs which have fewer, let's say, number of arrows. They are usually subgraphs of V. So that means that this procedure is recursive. So you can compute recursively the antipodes, and this is a sort of a convolution formula. And so I've exhibited these formulas right here. So S of dot is the minus dot graph, simply because this dot is a primitive element again. And remember, for primitive elements, S of x is just negative x. S of 2 dots is just 2 dots. Actually, S is a morphism of algebras, it turns out. And so therefore you get to the second row from the, so this row, we have this row over here. Let me see, we have this row over here. Sorry about that. And then the second row follows from the first. Then you do a little bit of computation and you can get, yes?
When you say this row over here, I don't see anything.
I'm highlighting as I go. So I'm
Is that
saying,
what you're doing? Oh, okay. Okay,
yeah.
thank you. No, I'm looking for
Sorry.
a pointer. Thank you.
No, sorry. So I, unfortunately, with OneNote, at least I haven't yet figured out how to do pointers. Yeah, so I'm saying, okay, I have this because dot was a primitive element. Then I have this row here because S is a morphism of algebras. And then you can also get this row by looking at the formula that I did before, and that's all we need in order to find an S of V. So I just use the formula that I have over here, and then I just come with it, and I get this. So it's just a little bit of computation. You can, it's not that important to follow up exactly how things come together. What would be something that's interesting is to note, I didn't want to write the whole formula from the beginning, but one thing I wanted to write is that, for example, you see we have some terms that appear twice, like, for example, these 2 terms. So there's going to be some sort of regrouping, and there's also going to be some sort of cancellation. If you look in the formula in this row over here, let's see, we had actually this term and this term which cancel out. Just use these 2 formulas, and you'll see that they actually cancel out. The first term here will be just negative dot dot dot, and the second term is positive dot dot dot. So the point is that when you compute the antipode with these formulas, while you can write it down, there's going to be possibly a lot of cancellations and a lot of regrouping that's going to happen. So that's the spirit of the main question. Can we find a cancellation-free and grouping-free formula? And combinatorial Hopf algebras have been looked at, looked at by many people: Aguiar, Ardila, Bergeron, Mahajan, Soti, and many others, and even with a lot more generality. So what we really want to do is to find, for such algebras, to find combinatorial bases of primitive elements, and again, cancellation and grouping free formulas. So I'm going to go over this for graphs, which is not really new. At least the basis of primitives have been already obtained before. The novelty is going to be in the more general setup, but I want to explain just the setup on graphs, and then I'm going to go a little bit over the new result. So again, yeah, so this is something that I forgot to make math from. So I'm going to define this map P that really goes from H to H. So this map P, you take a graph G and you define PG to be this element that I define right here. So the sum over the subsets of the edges, you take -1 to the E, and then you take the C minus E. That's supposed to be the isomorphous type of graph that you get by removing the edges in the set E. Okay, so in this sum, is perhaps in order to understand this, we'd have to realize that first the sum, first you fix the graph and a labeling of the vertices. So you go with all the subsets of the edge set. But then here, when you actually write the terms of the sum, all you remember is the isomorphous type. You don't, you don't care about the labelings. You just forget that. So that's why I wrote these square brackets here. So here's an example, P delta. So again, delta is the triangle graph. So let's just look at this example here. So what do? You're supposed to take out edges, and depending on how many edges you take, you put a plus or a minus. If you take an odd number of edges, you put a minus. And if you take out an even number of edges, you take a plus. So first of all, the delta appears as it is. You take nothing out. Then if you take one edge at a time from the triangle graph, you get this V graph. So, and that's one edge, so that's a negative. So you get 3 times the V graph. If you take 2 edges out, that's the second term over here, then you get 3 graphs of that type, and that's that term. And then finally, if you take out all the edges, you get this last term, which is just the totally disconnected graph. So here's a little lemma. This P extended linearly, because I just defined it on the isomorphous types of graphs. This T is in fact the morphism of algebras. And these are primitive elements if and only if G is a connected graph. So PG are primitive elements if and only if G is connected. And again, the reason for which we are wanting to look at primitives combinatorially here is because they have to do a lot of with these conjectures, but not only. But from the Hopf algebra perspective, primitives are the ones that control the algebra. So remember that this algebra is isomorphic to the algebra of polynomials, but there in the algebra of polynomials, we have the variables are primitive. So those completely describe the structure. So we would like to know, in this algebra, what are the primitive elements? And note that as an algebra, I could already say it's isomorphic to the polynomials, where the basis is just the set of connected graphs, isomorphous types of connected graphs. But those are not going to be primitive elements. So that's not going to describe an isomorphism, a structural isomorphism as a Hopf algebra. So that's why I want to find a basis of primitives. And I want to find, hopefully, a good basis which will have some combinatorial significance. And here's the next lemma, which kind of goes that way. So it turns out that every graph can be expressed like this. You take a graph, and now this graph in terms of these elements P, it's a sum over the set of edges, over a subset of the set of edges of P, and again, G minus E is a notation where I mean just the graph obtained from G by removing the edges in the set E. So consequently, sorry, there's a little typo here. So actually, it's a good thing that I can now edit like this. So consequently, I can write H in terms of these pHs exactly like this. It's H is going to be a sum over isomorphism types of these numbers, which I call G divide H or G period semicolon H times pH, where that is supposed to be this G semicolon H is supposed to be the number of subgraphs of G isomorphic to H. So that completely describes G in terms of these things, and I can even break up H into connected components, and that actually gives me an expression of the graph G in terms of these pH. And so it turns out, as I said, these pH are primitive elements, and in fact, they provide a basis for the space of primitive elements. So this is, in fact, a combinatorial basis. So each G is actually expressed as a combination with non-integer coefficients in monomials on graphs. And as I said before, this G divide H is just the number of subgraphs of G isomorphic to H. And here's just another example where we have computed this P delta, and then delta here can be computed like this. So it's P delta plus 3PV plus 3 times P corresponding to dot and I, but this term here can also be written as P dot times PI, because as I said, this is a morphism of algebras, and this last term over here is just P dot cubed. So this is a polynomial in the elements PG, where G is a connected graph. So the elements PG for G connected behave exactly like the variables in the polynomial ring, where I define them to be primitive. So that gives us the basis that we were looking for. It also has combinatorial significance because the coefficients that appear here are exactly these coefficients recording the number of isomorphism subgraphs isomorphic to some H. And then we also have a consequence with the antipode. So I probably won't dwell too much on this computation that I did here. But the only thing I want to remark is, why is it now very nice that we can apply it to such things? And the key is that, remember, if you have a primitive element, the antipode of a primitive is just negative, taking the negative. So if I want to find some sort of a formula for the antipode that really is given in terms of the graph basis, so I apply S to a graph here, then I write the graph as I did before, as in terms of these P's. But now when I apply S to these P's, it's very easy to do that. So it's just the sum of the P's, and then there's going to be some coefficients, -1 to this number C G minus E. Why is that the case? Because each of these PG minus E are graphs which are possibly not connected, so they decompose into a number of connected components, and this is what the CG minus E is, the number of connected components. That means that the graph itself is a product of C many connected components, and when you apply S to each of those, you pick up a negative sign, because each of those are going to be primitive. And then once you do that, all you have to do is then take these PGs and apply the formula again that takes you back in terms of these graphs G, and then you can reorder these and finally get a formula with coefficients explicitly written in terms of these numbers. So you can find such a combinatorial formula, and you can make it cancellation free by just putting together eventually isomorphous types. Okay, so that's the story here. So here's another way of writing this formula, this green box right over here. So you can write this sum over like connected subgraphs in such a way that D1, D2, dk is a subgraph of G, but this less or equal is supposed to be just this is a subgraph of G with the same number of vertices, and you have a sum of -1 to the k, and then there's some other coefficient over there, and then there's some coefficients that record the multiplicity. So anyway, as I said, I don't want to just dwell on this formula too much, but the main point is that now this process allows us to obtain exactly what formulas we were after. So these were the computations that I did before, where I had S of delta computed like this in a manner that's grouping free and cancellation free, and S of V. So so now we can get these formulas for graphs. Okay, so the last thing I want to say is a general combinatorial setup where we can do this for other type of structures. So there are such Hopf algebras or such algebras that you can define for multigraphs, for so for graphs, as we've seen, for multigraphs, for hypergraphs, for simplicial complexes and delta complexes. So we introduced this this structure that we call a multicomplex C, which is just a collection of possibly repeating multisets that are based on a set NC like this, and together with a partial ordering, which have two properties. The singletons K are supposed to appear among these AIs exactly once, and they also, the singleton K is contained, if K is contains in the set AI, then we declare that it's comparable. So we have a partial ordering here. And if two sets are comparable, then AI has to be contained in AJ, but not vice versa. AI can be contained in AJ and not be comparable. So intuitively, you can think of these as the AIs as some sort of a faces of this multi-complex, and the ordering as some sort of an incidence relation. So here's such an example where you have just a set based, just a multi-set based on the set 1, 2, 3. And we have 8 faces here. So 1, 2, 3, the vertices are supposed to be in there. 1, 2 repeats twice, and I've drawn this here on this picture by having 2 edges between 1 and 2, and they have the edge 1, 3, the edge 2, 3, and then you have this face 1, 2, 3. But this picture that I drew here, see, I ask that the relation is given by inclusion, except that we declare A5 and A8 are not related. So the edge that I drew a bit more curved here, which is A5, is not supposed to be related to A8. So that's not a subset, is not sort of a face of this, let's say, 3 simplex here. So the 3 simplex that I hashed here is 1 3 simplex, and then the other one, and there's another edge there. So you see that this way you can encapsulate with this definition delta complexes and also simplicial complexes, hypergraphs, because in a hypergraph you can have these sort of edges that are simply just subsets of the vertex set, not just 2-element subsets, and multigraphs where you have double edges and things like that. So just I've listed here a number of modifications that you can take, in which you can take once you can get a multigraph, you could get a delta complex or a simplicial complex if you do, or even a hypergraph, or you can get a hypergraph in several ways. So for these multi-complexes, so as I said, they contain many other things, even things like colored simplicial complexes and things like that. There's a natural notion of, as you might expect, of a sub-multi-complex, so a sub-object, and also a natural notion of an induced sub-multi-complex, as you would expect. You just take a subset X, and then you preserve all the faces that you have, C restrict to X. You will just preserve all the sets that are supported on that X. So that's just simply the induced complex. And there's again a similar type of algebra for these multi-complexes, and the multiplication and co-multiplication will be the same. So if you take 2 CD, you want to multiply them, you just create a new multi-complex by just putting them together, just a disjoint union of their vertex sets, and then also of the faces, no new faces, and no new incidence relations. And the co-multiplication will be exactly the same. You take a C and you just break it up into all possible pieces according to the vertex set, and then you take the restrictions. So here you take everything again, everything up to isomorphism. And we will write something like C less or equal to D if C is a submulti-complex of D, but with the same number of vertices, so base with the same number of vertices. So let's see, let me just formulate the general result. So again, as before, I'm going to define some elements PC. So these are going to be the elements. So these are going to be sum over submulti-complexes of C, but again, with the same number of vertices. And I need to use this mu dc times d, where this mu is the Mobius function of the pose set of exactly of such subcomplexes of C based on the same number of vertices, and when with this natural subcomplex ordering. And the theorem is that this assignment C goes to PC. This is supposed to be an arrow, but I think we all know LaTeX. So C goes to PC defines, in fact, an automorphism of AC. AC now HC is going to be just the span of all these isomorphous types of multi-complexes. And again, PC are going to be primitives exactly when C is connected. You can define a natural notion of connected multi-complex, as as you might suspect. And again, we have similar type of formulas that C is written in terms of this basis, and you can actually write it concretely in terms of isomorphous types. Each multi-complex is written as a sum of PDs, where you get these coefficients again of the multiplicity of D inside C. And the sum is now over isomorphous types. So really, this is a sum as expressing of C with respect to this new primitive basis. The point is now that we can do everything that we did for graphs, and we can get such formulas for multi-complexes. But now these formulas particularize to get formulas for graphs, for multigraphs, for hypergraphs, simplicial complexes, and so on and so forth. And there's some other consequences that we can get. We went back to the reconstruction conjecture. We wanted to see what we can prove. We could prove some things, but still, we're not. I don't think we're close to being able to do something like significant. We could reobtain, for example, that for disconnected graphs, they are reconstructible, or you can reobtain that. Let's see, that the vertex reconstruction conjecture implies the edge reconstruction conjecture, or you can even reobtain the fact that trees are reconstructible, although we did not write that in the paper because it didn't feel like it's that really that much different somehow, the proof in its core. So so we're still hoping to be able to go back to this and think some more. But I think the main thing of our work is that a lot of these formulas that we get exactly these cancellation and grouping free formulas that are thought they are really what one wants to find in these combinatorial Hopf algebras, and the basis of primitives for this general type of Hopf algebras, combinatorial algebras, that can then reobtain a lot of these formulas for particular cases. Okay, so that's yeah, I guess that's the end of my talk. I don't know if I went hopefully I didn't went over too long. So thank you very much for everybody for participating and for listening. Thank you.
Let's thank the speaker. And let's open the floor for questions. I end the recording and you can speak.